Assalamu alaikum wa rahmatullahi wa barakatuhu. Hi, I'm Yasser Alsam. In this video, I will demonstrate the SAP-1 architecture-based 6-bit computer design and implementation project from EEE 4308. Here we have integrated different types of module with a 6-bit bus. So at first we have a clock module which will pulse continuously 1-0. We have a program counter which can count from 000 to 111. Here we have a memory address select register which will take 3-bit address from program counter and send it to the RAM. We have a input unit which can input addresses and datas to the RAM. We have a RAM which will store the address and data. We have an address selector which will select input from input unit and memory address register and give the output to the RAM. We have instruction register which will receive and store 6-bit instruction from RAM. We have a controller sequencer which will control the other modules by outputting some signals. We have accumulator B register. Here they will store the data we will input, and the arithmetic logic unit will process the data by adding or subtracting. At last we have the output register which will show the output in binary values. But not but the least, we have added a 7 segment display additionally for our additional case to show the value in decimal digits. Now I will demonstrate how can we process, add, load, halt the data. At first we have to simulate it. By simulating it, we have to off the clock. We have to reset. Click the reset. One time will be preferable. And then we have to, at first we have to load some values in the registers, in the accumulator, in the B register. At first we will load the value in the RAM. We will load the instructions for load. We will save the instructions for load, for halt, for addition, for subtraction, and for output. Now we will start with our operation. First, we have to load the instruction. For loading the values, we know the opcode is 000. So we will input 000 and the address will be 100. And the address selector is 000. We will read it. Again, for addition, the opcode is 001. We will save it at 101 and the direction is 001. And the opcode for subtraction is 010. We will select the address as 110 and the direction will be 010. Then we have to show the output. For output, the opcode is 011, and here we will ignore the address. And the direction will be also 011. We will read it and we will give the process as halt, we will stop the process, and for that we will give the opcode as 111. Also here we will ignore the address. For address selector we will use 111. We will run it. So for addition we have got the inputs. Then we have to give some 6-bit data for addition. We can give 16 and we can give the instruction load. We know we have saved the load in 100 address, so we will give 100 as address and we will run it. Again we want to add 8 with 16. We will give the addition instruction address and we will run it. Now we have to run the program and we have to switch on the auto clock. As soon as the halt is 1, we will end up with the process, and our process has been end. We have got our output as 24, and we know 16 plus 18 is equal to 24. Again, we want to subtract some values. We will give all the things as 0. We will stop the simulation and again run it. Here we will reset it a couple of times, and then we will instruct the inputs. Here again we will load. We want to load, so we want to instruct the save the load instruction 000 at 100. We will run it. Again 001 at 101. Then we will give it at 1001 and we will read it. Again we will do the same thing. 011 we will give subtract opcode for 011 and we will save it at 110 010 and read it. We want output 011. We will ignore the address. We will give that direction 011 and we will read it. So for addition and for getting the halt, we will add 000 and ignoring the address, and we will add the address direction will be 111. We will read it and we will give some values. The value can be 12. We will load it, and the other value can be 8. We will subtract it as 110. Then we will run the program. We will turn on the auto clock bus. We will have some value when the halt is 1. We have 4. We know if we subtract 8 from 12, we will have the value 4. So we can see we have done the operations for additions and subtractions for 6-bit data. Here we have optimize some instructions as we see at the control sequencer. Here we have 5 JK flip-flops, but we have T states, 6 T states, 1 1 2 3 4 5 6. So we have lessened the T states from 6 to 5. As we can see, there is 1 2 3 4 5. If we change the clock, add a new one for some issues, and if we run the clock, we will see the clock is generating one by one as we want. So here we have the opcode input. As we know, for 000 we will load the value, for 010, for 001 we will add the values, for 010 we will subtract the values, for 011 we will show the output, and last but not least, at 111 we will hold the process. So all the 5 instructions are coming from here. When the instruction matches one inputs, it will turn into 1 and we will have the value, and we will get the 1 value at the control outputs. As we can see, for load we have CO and MI at the T1 state. So if we turn on the load, if we give 000 opcode and run it, we are having CO and MI at the T1 state. If we describe it, we can say when the T1 is on, the first one is on, we can have some demonstration. Yeah, okay, we will wait for the T1 state to be on. Yeah, when T1 is on, this wire is at 1, and from this wire we have this IO, and we have MI, and we have CO. So we know at T1 state the instruction, the output instruction CO and MI will be at 1. So we can see the input of MI, one of the input of MI is coming from the 1, from number 1, and one of them from 1, here we see, and one of the input for CO is coming from also 1. So this way we have integrated all of the instructions one by one and got these outputs. Here we see we have converted T2 and T3 into T2. So we have reduced it from T5 instead of T6. For T5, for T2 and T3, we have combined this output CE, RO and II. So for CE, RO and II, we have CO, MI. For load instruction, for the second state we have CE, RO, II, where the program counter is incrementing the counter, and the input register is giving the output to the RAM. So if we go to the next state, in T2 we will see we have a wire for CE and II, and a wire for RO. So CE, II, RO are at one state for the T2 state. So we have reduced the state by doing and thinking like this. So here we designed the control sequencer like this. So for the full SAP project, we have found some integration problem as we designed it separately. Nevertheless, we have integrated it with clear views, and we have solved some problems regarding the designing of the modules. So here we do the project. Here we have done the project for 6-bit for the SAP-1 architecture based 6-bit computer design and implementation. Thank you very much for watching this video. Assalamu alaikum wa rahmatullahi wa barakatuh.